Hi, I'm Hidy,
I'm Lena Williams.
and we would just like to thank you for coming to see our Capstone project Platypus printing. Like I said, I'm Hidy. I'm a senior here at Grandview. I'm involved in Women in STEM, robotics, teens reaching out to homeless teens, and Puzzle Club. I've also been involved in TSA. Next year, I plan on going to Colorado School of Mines to study mechanical engineering.
I'm also a senior. I am also involved in Women in STEM, robotics. I'm the founder of Puzzle Club, and I've also been heavily involved in technical theater. And I will also be attending Colorado School of Mines in the fall.
Here are our advisors.
So this is our expert advisor, Camden Young Scoville. He graduated from Grandview High School and then attended Montana State University and graduated with a degree in mechanical engineering. And now he works at ASML as a mechanical design engineer.
These are some of our support advisors from our class. We call them the board. They helped us with emotional support and keeping us on task. And then we have some more support advisors too, previous students from last year, and then our parents who helped us with emotional and financial support. And then here's our inspiration for the project. We both really love 3D printing. We both have 3D printers ourselves at home. And we love how versatile 3D printing is. And then it's growing in the engineering industry for uses. And so we just wanted to see how it works and really understand everything about 3D printing.
And you can see on the right there are my 3D printers, and on the left is Bella's 3D printers. So we're pretty familiar with pretty standard 3D printers, and we're both very passionate about this project.
Here are my 5 project objectives. So my first one is learning how to code, because I knew, even though that I was going into mechanical engineering, that I needed to learn how to code so that I could do certain projects within engineering. My second one is to learn better time management skills, because I am a huge procrastinator, and I knew going into college that I needed to stop doing that. I also wanted to learn more materials specifications so that I could take this into my engineering career and just have a broader knowledge of that. My fourth one is to get better at public speaking, because I knew it is a very important skill throughout life, and I also wanted to gain a deeper knowledge about 3D printers so I could take it and maybe specialize in something 3D printing.
So for my project objectives, I wanted to develop better organizational skills because I'm going to be going into college and I want to go in with really solid organizational skills. I also wanted to gain a deeper understanding of just the parts of a 3D printer, what goes into it, and how each of those parts work. I also wanted to learn a little bit of code. I've never really taken any coding classes or anything like that, so I know very minimal code, and so I was hoping to learn a little bit on this project. And then I also wanted to learn how to actually build a 3D printer from start to finish, the process, the order, and what goes into that. And then finally, I wanted to learn some 3D printing industry standards and expectations so that I know that if I go into that in the future, what is going to be expected in that industry.
Before we started our project, we wanted to really understand everything that was going on so we knew exactly what we were doing. So we started with our initial research.
So for our initial research, there was a couple things we wanted to research, but one of which was what kind of 3D printer do we want to make? So there's many kinds of movement systems for a 3D printer, but the main two, or at least the most common two that you'll see, are Core XY and Core XZ, also known as Cartesian. So Cartesian printers are what you think of when you think of a 3D printer. They are one stepper motor per axis, so each stepper only controls one axis, and if you move one stepper, it will move in a straight line. This has some benefits in the sense that these are often much cheaper, they're more readily available, and they're a lot simpler to repair and replace parts on. But they also can't go as fast or as accurate as something like a Core XY. Now, a Core XY, which is what our printer ended up being, is a printer where the Z-axis is on its own stepper, but the X and Y axes are linked. And this is great because it means that you can print a lot faster and a lot more accurately, but it's also, they tend to be a little bit more expensive and more challenging to build. So here you can see a little diagram of how each of the movement systems work. So on the Core XZ, you can see that it's just one direction per stepper motor. But on the Core XY, since the X and Y are linked, if you were to only move one stepper, it would move diagonally instead of in one direction. And so if you want it to move in one direction, you have to move both at the same time. If you move the x-axis, if you want to move the x-axis, you move both of them in the same direction, and if you want to move the y-axis, you move them in opposite directions.
Next, we wanted to know how the 3D printer itself is programmed. There are many different flavors or types of G-code. G-code tells the printer how to move when and where. The two most common types of G-code are Marlin and Clipper, Marlin being the most commonly used one of those two.
We also looked into what the basic systems were of a 3D printer. So the first system we looked at was the framing. This is just the basic structure of what holds the whole printer together. Then we looked at the movement, which is going to be any parts like belts or rods that allow the printer to move. Then we have control, which is going to be your motherboard or your screen, things that allow the printer to actually receive data. Then you have your heating elements, which is usually on the 3D printer, your bed and your extruder, which help the filament come out and stick to the bed. And then you have your electrical, which is any wires or sensors that you might need to connect it all together. And then finally, of course, software, which is what tells the printer what to do with all of those other parts.
In the beginning, we made a parts list so that we could keep track of what parts we had and what parts we needed to get and how much they all cost. In the beginning, we put a bunch of parts in this list so that we might need and so that we could keep track of everything. After this initial research, we knew exactly what we wanted to do with our project. We wanted our printer to be Core XY encoded with Marlin. We wanted it to be cost effective with a large build area and also have good print quality. Here's our original timeline.
So our original timeline was extremely ambitious. We thought that we knew a lot about 3D printers, and so we originally thought that we were going to be doing most of our research in October and November, and then we were going to move on to building the basic printer by winter break, and come back in January, begin coding the printer, testing it mid-January, and then by end of January into early February, figuring out other things we wanted to add onto it, like more advanced features. And then we were going to, in mid-February to March, we were going to actually build those features. And then in late March, we were going to code those features. And then in April early and mid-April, we were going to test those features as well as design our presentation.
After our initial research, we jumped right into dive deeper into all of the systems. First, we knew that we needed a frame for this 3D printer. We started researching a bunch of different types of framing for 3D printers, and we found that 80/20 was the most commonly used of those framing pieces. This is because it is very versatile in both size and shape. It's also very easy to connect things to because of the T-slot mechanism in the middle. As you can see here, we have the original dimensions for our frame. These did end up becoming bigger at the end because we needed more space for the size of our bed and all of the movement. We also had some problems with building the frame because our original design for our connection pieces were just too weak and they kept snapping, as you can see in... As you can see here in this picture. And then we made it out of PETG with connecting pieces that screwed directly into the frame. Now, there were some crackings, but Lena was able to solder them back together and they're still working perfectly fine.
So the other parts of movement that we had to consider were the actual motors that were going to move our pieces around. And so 3D printers typically use stepper motors. And this is because the steps, rather than just like degree turns, help printers get more accurate movement. And most stepper motors that are used by 3D printers are bipolar, but there is also unipolar motors, and that has to do with how many coils are inside of the motor. And the typical standard degree of a stepper motor is 1.8 degrees, which means for every 1.8 degrees it turns, it moves one step. So we knew that we wanted something that was fitting the standard profile of a stepper motor, so we ended up going with NEMA 17, which is a frame body size. It's a standardized size of 1.8 degree bipolar stepper motors, so that they would be nice and easy to integrate into all of the rest of our things.
Now, connected to these stepper motors are timing belts, especially for the X and Y axes. These timing belts have teeth on the inside of the belts that mesh with the gear that's actually on the stepper motor. This allows movement by turning the gear and meshing with the teeth on the belt. This helps with the accuracy of the print.
We also knew that we needed some sort of thing for our axes to slide on. So we decided that we wanted to go with rods, so we looked into what standard 3D printer linear rods look like. So standard 3D printer linear rods are 8 millimeters in diameter. They're a smooth stainless steel rod, and then you use linear ball bearings, which are essentially just a hollow cylindrical piece of metal with tiny balls on the inside that you can then run on the outside of your rod so that anything you attach to those ball bearings slides smoothly across your rods.
Next, for our Z-axis, we wanted a plate under our bed that could raise and lower on the Z-axis. Now, we wanted to make sure that it was strong enough to be able to support the bed and whatever it was printing. Our advisor told us that we should use Young's modulus. This is an equation to calculate the deflection of a certain type of material based on the weight that's on top of it and the points of connection on the plate. Here you can see our original design for the rods for the X and Y, and then also the original sketch for the top connection pieces that the Y rods are connected into, which you can see in this picture. And then also on those rods are another type of ball bearings that have screw holes in the top that we connected our X-axis to later. We also had to cut down our rods because the only ones we could find on Amazon were 450 millimeters, but we needed them to be cut down so they could fit within our size constraints. Next, we designed the stepper motor mount for the X and Y axes. We were able to design this first try, but we forgot to add tolerances, and so we did have to do quite a bit of sanding to get them to fit, but after all of that, we were able to get them to fit in.
So the next part that we had to research was the hot end. A hot end on a 3D printer is the part that actually has the filament run through it and heats up so that the filament can extrude out. We looked at a couple different kinds of hot ends. There's two main kinds of hot ends. There's PTFE insert hot ends, and then there's all metal hot ends. So all metal hot ends are like this one you see down here, where the PTFE tubing, which is essentially a high temperature plastic tube that guides the filament into the extruder, it stops above the heating element so that it's all metal where the actual filament will be getting hot. PTFE insert tubings, the PTFE tube goes all the way down into that hot end. PTFE inserts can only get up to around 250 degrees Celsius before they start to degrade. So all metal hot ends are great if you want to have a higher temperature printer. But for most applications, PTFE inserts are fine because most filaments don't really need that kind of temperature. And PTFE insert hot ends tend to be a little bit cheaper. So we decided to go with the standard Ender 3 hot end, which is a PTFE insert because we were both familiar with it as we both have an Ender 3. And also, we really didn't need those kinds of temperatures for our build. We also then needed a box to put our hot end in that would actually become our chassis that would ride around inside of our X and Y rods. So the first step was we drew it out on our table. In the engineering rooms, they have whiteboards, and we drew it out and we marked out all of the dimensions. And then we actually found a sheet pan at Goodwill, and we cut it up into our sections, and then we glued it together, and that's what you can see held together here by the Mountain Dew cans. And then once that was glued, you can see the final result with everything mounted in there. So then the last step of building this chassis was to actually put what we've been calling the cap on it, or essentially just a piece to close off that open side and also sort of hold everything together. We also needed our timing belts to be able to connect to this so that we could tension them through to our chassis. So we again drew it out on the whiteboards, and then we designed it up in CAD, 3D printed it in PTG, and then as you can see here, the timing belts are coming out of the sides of each of this cap piece.
Here you can see the full X and Y rods with the aforementioned extruder box, and then here's the full X and Y with the timing belts tensioned and the extruder inside of the box.
So after we finished our X and Y axis, we had to move on to our Z axis. Now we needed a metal plate that our 3D printer bed could actually be attached to and ride on. So what we did was we did some calculations that our lovely advisor gave us to try to figure out what size, or what thickness rather, of metal we would need in order to have our bed not bow or bend in the middle. So we ended up getting a 16 gauge weldable steel plate, and we cut it a little bit shorter because we got a 12 by 24 sheet, and then we just had to cut it down a little bit so that it wouldn't stick out the sides. And that was going to be the plate that was going to ride up and down on our z-axis.
After we cut it, we had to drill holes for the different types of rods for the z-axis, the linear rods and the screw rods. The linear rods are there so that it helps stabilize the z-axis while moving up and down, and the screw rods does the movement itself. We JB welded the linear ball bearings for the linear rods onto the plate. And then we screwed in the screw rod inserts with the already there screw holes. And then here you can see the top of the x-axis. With the linear rods have the caps on the top so that they can stay straight up and down, because if they didn't, then it would cause Z-banding, which would make our Z-axis completely stop and not be able to move. The screw rods, however, do not need these caps and can just sit there free floating. And then the next picture, you can see the bottom of the Z-axis, which have the caps for the linear rods again that hold them in place. And then the screw rod is connected to the stepper motor using a coupling, and it directly moves the screw rod.
So we also knew that we were going to need a bed for our 3D printer. Now 3D printer beds are typically made of a heated aluminum plate, and we knew that we definitely wanted our bed to be heated for adhesion issues. But we also knew that we wanted our bed to be a relatively large size, and so we would have a relatively large build volume. So we decided to go with a 310 by 310 bed, and you can see here that this is our bed without anything on it, and you're not supposed to print directly onto this aluminum surface because it just doesn't stick right and it will adhere forever if it sticks too well. So there's two main options that people use for the actual surface that you print on. Usually it's either a glass plate or a PEI coated metal flexible plate. We decided to go with this magnetic flexible PEI plate because it's very easy to remove. You can bend the plate so that it makes prints come off easier, and they are a little bit cheaper than glass plates. And then you can see we attached it to this metal piece via some screws and some springs so that we could actually level it by each corner manually. And then this is the final look without and with the PEI plate on it.
Next, we had to research our power supply. From previous parts we had already bought, we knew that we needed 24 volt and 20 amp power supply. This is so that we had enough power to go through all the parts but also not fry them. And then for the stepper motors, they need stepper motor drivers to tell them what to do. We went with the TMC2209 because with our motherboard, it was compatible with our motherboard and our steppers. Also, our motherboard has a UART mode, which is very powerful and very accurate. And
so then after we got all of these electrical components and our basic frame was built, we had to actually wire everything into our motherboard. So this is a little diagram I made of just where everything is wired. So over here, you can see our power bank. We have our input power for our board and our motors, our input power for our bed, and then the bottom one is our output power for our bed. Up here we have those stepper motor drivers. They correlate to what number slot the stepper motor it is controlling is in. So we have up here our X and Y stepper motors in slot 0 and 1. And then we have our Z stepper motors here, which are actually in a special linked slot that is slot number 2. Both of those slots are slot number 2. That's why there's only one stepper driver controlling those two motors. And that's so that we can have a dual axis, or a dual stepper motor Z axis. That way it will move at the same time. And then we also have our extruder right here, which is in slot number 4 because that's what Marlin basically supported and we didn't want to make our life harder. And then we have our screen, which is connected via 2 cables that give power and signal to our screen. And then down here we have our thermistors, so our hot end and our bed thermistor are plugged in there. Just below that we have our limit switches in this purple box. And then those allow us to home in the upper left corner so that it knows where 0 is. Down here we have our fans, and then last but not least, we have our extruder, I should say our hot end power.
next, we knew we had to code our printer. So G-code, specifically Marlin, has 2 types of commands: G commands and M commands. G commands tell the printer how to move and when. M commands set up the basic configurations of the printer, and then there are more configurations that you have to do but we'll get to that a little later. The normal syntax for G-code is the command type, command number, parameter name, and parameter value. This command is telling the printer that it needs to move the x-axis to the coordinate point 23. Next, we needed to do configuration, which is setting up all the hardware that we use, like the motherboard and the stepper motor drivers. We also needed to set the build volume for our 3D printer. We also had to tell it how many rotations the stepper motor needed to do for 1 millimeter, and then telling it what axes the printer had. We had some problems come up with this, which was caused by two major problems. First, our stepper motors were not wired in the traditional way. The traditional way to wire a stepper motor is A1, A2, B1, B2 for the two different coils, but our stepper motor was wired A1, B1, A2, B2, but our board was wired in the traditional way. So when we plugged it in, it was only sending half the power to half the coils and telling the stepper motor to move in two directions at once. Now, we thought this was a lot of other problems with our configuration, and we spent roughly 6 hours trying to figure out what was wrong, but nothing was working. We tried different modes from our motherboard and a lot of other things, but then we checked our wiring diagram and saw that they were wired differently, so we just swapped some of the wires around in the connector, and it worked after that. Next, when we configured the Z-axis originally, we had the home positive position at 340 because it was at the max height. But when we put it into our slicer, it got confused and kept trying to push the Z-axis up more when it physically wasn't able to. And so we had to switch the direction of the Z-axis so that it would go down, and switch the Z-axis homing, and also set the home position back to 0 so that the left corner is 0, 0, 0. Here's our new timeline because we were very ambitious with our old timeline. So pretty much the whole entire first semester was researching and buying parts. Over winter break, we designed the parts for the frame and started putting together. And then in January, we put the full frame together and started troubleshooting all the problems that came up with that. And then mid-January to mid-February, we started working on the X and Y movement. And then we worked on the hot end assembly in mid-February to mid-March. And then mid to late March, we started working on the Z movement. And then after that, in April, we worked on coding and wiring. And then on April 20th, we were finally able to test print it, and it worked, and it was great. And then also, during April, we were working on presentation building.
So overall, we were able to accomplish a 3D printer that can actually print something. As you can see, that is a calibration cube. Excuse me, sorry. That our printer printed. And while it isn't the most amazing quality in the world, because we didn't have time at the end to calibrate, we are very proud that it was able to produce anything at all, especially because of just how fast we pulled the end of this project together. And we feel that we've learned a lot about 3D printers and the engineering design process in general. I mean, we had so many times where we had to design something out, reiterate, go back and change things and then test it again. And we really never stopped doing that throughout the whole process. And we just feel that we've learned so much through this experience. And if we were to do it again, we think that we would be able to do it way better and way more efficiently.
To end off, we would like to quote our advisor, Cam. There's no crying in baseball, but there's a lot of crying in engineering.
This is our bibliography. Does anyone have any questions about our printer or our project?
Colton?
Which one of you is taking the printer home?
Probably me.
Yeah. Parker?
For your print bed, did you guys use adhesives, or was it good enough with the heating bed that you had?
It was good enough with the heated bed that we had. Right?
If you had 1 more month, what would you do?
Probably dial in the calibrations of the slicer and then maybe start working on other features.
What was the hardest part of the process?
I would say definitely the framing, even though it doesn't seem like that would be the hardest part. Just conceptually trying to think about making a printer from literally nothing, we went through many iterations. If you come to our table in the back, you can see we have a lot of older parts that we have either broken or they just didn't fit quite right. And so we kept having to reiterate and redesign those connection parts.
How much were all overall costs?
Like around $470, which comparatively to an XY printer of this size, that's not a lot. Harriet?
How do you guys think your project would have differed either in process or result had you worked alone instead of as partners?
I think that there's certainly no way we would have been anywhere close to this final product if we worked alone, because while for a lot of it we were both just working on the same thing, there were so many different tasks always to be like getting done at the same time that, especially in the later stages of this, I began wiring while Bella started configuring all the code. So honestly, alone, I think it would have taken about double the time, so I think we would have had about half the product.
Do you think that by working together, like obviously you said your advisors helped you stay on track, but do you think that productivity-wise it's been an apple partner?
I think so, yes, because it wasn't only depending on my grade, it was also making her grade, and so I didn't want to ruin her grade.
If you could go back, what process would you change about building?
I think if we could go back to the beginning, I think padding out all of the framing and the parts for the like connection parts for that framing first would have really helped us, because we spent quite a lot of our timeline just putting things together and trying it and stuff. And if we had just done the actual CAD pieces, like you can get the like 80/20 we're using, you can get the files for that and you can like put them together. And I think if we would have done that in SolidWorks first, it would have been a lot easier to actually get that initial frame down.
Would you do this again? Is it valuable enough?
I absolutely think
Yeah.
so. I intend to at least build another 3D printer in my life. Maybe not this exact Core XY style. Maybe I'll try a resin printer or like one of those weird ones like does it in the goo. Yeah, I think it would be a very fun project to do again, and I feel like I have a lot of knowledge now that I could actually succeed with that.
All right, thank you.